Dear friends, welcome back to another episode in the series on geodynamics or dynamics of the earth. We have discussed in our previous two episodes the dynamic movements that take place on the earth's surface. We have seen how the various theories regarding the movement of the continents, the oceans and ultimately the lithospheric plates have been established with definite evidences. By plate tectonic theory can be expressed in the form of a cycle, then it will be better understood and better accepted. J. Tuzo-Wilson, the same gentleman who proposed the transform faults, the next stage of his proposed cycle, he said that because of the active continental margins, the oceanic crust below the ocean starts subducting and the ocean starts shrinking till the oceanic crust completely vanishes, like it has happened in case of India and Eurasia, forming the mountain chain of the great Himalayas, and finally the two continents on the two shores come close together, forming a suture with the ophiolite or oceanic crust emplaced along the suture. Though Wilson proposed this cycle to replace the orogenic cycle related to geosynclines, he did not name it on his own. The subsequent workers who were co-workers or students of Tuzo-Wilson, they called this cycle as the Wilson cycle. At this point of the lecture, it is not be irrelevant to refer to the comparison between the old orogenic cycle and theory of geosynclines with the modern day plate tectonic theory. In the geosynclinal theory, it was believed that there were two segments in a geosyncline, true geosyncline or orthogeosyncline. One called the myogeosyncline was found in the shallower parts where only sedimentary rocks were predominant and sedimentation was the dominant process. In the deeper part of the geosyncline called the eugeosyncline, together with thick pile of sediments, igneous activities in the form of plutonism and volcanism were prominent. But in the modern plate tectonic theory, there is no scope for a geosyncline. However, the terms myogeosyncline and eugeosyncline have been partly retained even under this theory. The myogeosyncline being replaced by myogeocline, the portion on passive continental margins where thick pile of sediments are deposited without any igneous activity, and the eugeocline is the deeper parts of the ocean basin where igneous activity is prominent. As we have discussed in the previous lectures and in the first part of this lecture, the plate boundaries of the three kinds are the most tectonically active zones on the earth, and only small amount of tectonic activity related to volcanism takes place inside a plate. These tectonic activities along the boundaries of the plates result in metamorphism, in magmatism and in the formation of metallic mineral deposits. In the next few subtopics, we shall be discussing these one by one. The metamorphism at convergent plate boundaries is very characteristic. Miyashiro, the famous metamorphic petrologist from Japan, first established that a double metamorphic zone or paired metamorphic belts are found across convergent plate boundaries. Taking examples from Japan, he showed that close to the trench where the dominant force is horizontal compression and it takes place at a shallow depth where temperature is low, in such zones where the temperature is low and compression is high close to the trench, we have high pressure low temperature metamorphism, while in the inside of the overriding plate close to the volcanic arc where the dominant factor for metamorphism is the intruding and extruding magmatic rocks causing increase in temperature, but where the horizontal directed stress is not that important, we have high temperature low pressure metamorphism known as the blue schist facies. This paired metamorphic belts at convergent plate margins was simultaneously reported from other convergent boundaries also. On the ocean floor close to the divergent plate margins, there is a low grade metamorphism mainly leading from the emplacement of high temperature new lithosphere and coming in contact with the cold sea water. Mostly hydrothermal processes are active during this metamorphism. Since the plate boundaries are the most tectonically active regions, magmatism or volcanism is also very prominent along these boundaries. Though there is very little magmatic emplacement along the transform boundaries, the divergent plate boundaries and the convergent plate boundaries together with the oceanic islands formed inside the plates are regions of volcanism. At divergent plate boundaries, as the mantle comes up close to the surface, the pressure is released and decompression partial melting of the mantle results in the formation of a basaltic melt, which varies in composition from olivine tholiites to quartz tholiites. This decompression melting of the mantle forms a linear magmatic chamber below the ridge crest, from which new lithosphere forms as it comes up to the surface. On oceanic islands, the rocks are also basalts or tholitic basalts, but there is a wide range of variation. Let us discuss about this variation a little later. The variation as reported from the Emperor Seamount Hawaii mountain chain is that the dominant basalt on these rocks is called the oceanic island basalt, which is tholitic in composition. Together with this, there are alkali basalts, there are mugiarites, a particular variety of basalt known as Hawaiite, then there are trachytes, quartz trachytes and phonolitic trachytes. These are all varieties of alkaline rocks or more alkali rich basaltic rocks. The apparent reason for this high alkali basalts is believed to be the source of the material responsible for the oceanic island volcanic eruptions. It is now believed that though at ocean convergent boundaries, the subducting oceanic lithosphere becomes one with the mantle below a depth of 670 to 700 kilometers, as there is no seismicity below that depth. It does not completely lose its mineralogical or petrological composition at that depth. It is believed that rheologically it starts behaving in a similar manner as the mantle, and therefore, there is no friction, development of strain and no faulting, not resulting into any seismicity below that depth, but physically they do not get dissolved into the mantle and may continue till the core mantle boundary or the D double prime layer, from where the deep mantle plumes originate. These deep mantle plumes incorporate these oceanic lithosphere into it when it comes up to the surface, and because the oceanic islands are formed in response to these deep mantle plumes or hot spots, the typical mineralogy and petrology of the oceanic island basalts are partly controlled by the oceanic lithosphere. As discussed earlier, the convergent boundaries are one of the most important areas of volcanism at the surface of the earth. Though the main volcanism takes place along mid oceanic ridges below the sea level, the surface level volcanism are most prominent along the subduction zones or convergent boundaries. Along the circum-Pacific belt or ring of fire, there are a series of volcanoes that pour out andesitic volcanic rocks. These are typical of this belt, and it is believed that the andesitic magma is produced by partial melting of the oceanic lithosphere at its contact with the hot mantle, and also the partial melting of the wedge shaped mantle that is trapped between the overriding plate and the undergoing subducting plate due to the shear heating, the heat generated by the friction between the overriding plate and the downgoing plate. This partial melting of the mantle wedge and the lithosphere are combined together to form the magma that erupts at island arcs or on continents parallel to a subduction zone. Hence, this variation in composition from mid oceanic ridge basalts or oceanic island basalts. Incidentally, the mid oceanic ridge basalts are fairly uniform in composition throughout and are called the natural mid oceanic or normal mid oceanic ridge basalts, but the exposure of the mid Atlantic ridge on Iceland, where there is a different type of mid oceanic ridge basalt which is known as the enriched mid oceanic ridge basalt or EMORB. Next we come to the metallogeny found at plate margins. Because of the tectonic activity at plate margins, various metallic mineral deposits form at plate margins. At divergent plate margins, where the extension results in the development of normal faults and tension fractures, the cold sea water moves down into the newly formed lithosphere and dissolves some of the metallic sulfides in the rocks below. As this hydrothermal fluid becomes hotter, it comes up through these pore spaces, and as soon as it comes in contact with the cold sea water, deposits the dissolved materials, resulting in the black smokers and white smokers, tubes emitting black smoke or a dissolved hydrothermal fluid or white smoke. These materials get eroded and rolled down as polymetallic nodules on the ocean floor. The other economic mineral deposits that are found at divergent plate margins are manganese oxide deposits, chromite deposits or asbestos deposits associated with the ophiolitic sequences, some podiform chromite deposits associated with serpentinized ultramafics, etc. Together with these, massive sulphide deposits of the cypress type are also associated with divergent plate boundaries. The metallic deposits that are associated with convergent plate boundaries are the base metal deposits of copper, zinc, lead, etc. Some precious metal deposits like the platinum group of elements, platinum, silver and gold, and the other mineral deposits like tin, antimony, wolfram and mercury. In some of the convergent margins, we find zoned economic mineral deposits or metallic mineral deposits. These are because as the lithosphere goes down along a convergent boundary, gradually metals are released from the subducting lithosphere and parallel zones of different minerals, different metallic mineral deposits form at the surface. Let us now see what we have discussed over this lecture. We have seen how transform faults are modified according to the lengths of the divergent or convergent margins they join. We have seen how the topography of transform faults vary according to the spreading rate of the divergent margin segments they join. We have seen why there are sometimes the formation of new lithosphere along transform faults. We have also seen how transform faults are related to strike slip faults, and there are curvature of oceanic lineaments near the transform faults. After discussing transform faults, we have looked at the metamorphism prevalent at the plate boundaries, especially the convergent plate boundaries and the divergent plate boundaries. We have talked about the magmatism, the kinds of igneous rock found at divergent and convergent plate boundaries, as well as on oceanic islands within plates that are related to the dynamics of the earth. Now, we have discussed how the metallic minerals deposits, economic mineral deposits of metals formed at divergent and convergent plate boundaries. That concludes our discussion on the dynamics of the earth, especially the movement of the earth. Thank you.